past the time, so I'll just go ahead and get started. Right. I haven't even worked out how I'm getting into this presentation. So I'm talking about Tiny Linux for IoT. This is going to be a fairly short presentation, but we want to talk a little bit about what some work that we've been doing within ARM that has been relevant to Tiny Linux discussion, especially the work that Nico has been working on the last few years. So when we're talking about IoT devices, there's of course lots of options: Linux, Zephyr, FreeRTOS, Embed, the various BSDs. Which you choose depends on how big your thing is. Was your IoT a tiny little node? Is it something as large as a Raspberry Pi? What is your software stack going to look like? The normal trade-offs of cost, complexity, functionality, security. This presentation is about Linux. This is specifically about Linux, a specific subset of those devices. I'm not going to go into all of the trade-offs on that. Where typically an RTOS is assumed for small IoT devices, because it's small, because it's easy to port. There's lots of devices available for it. There are a lot of scenarios where using Linux as your operating system just makes a lot of sense. It's got all that. It's got very robust networking functionality. It's got a process model. It's got wide application support, easy to port. Yet, we still need to be low cost, high volume, and secure. So how does Linux fit into this model when we're really constrained? And all of the Linux development has been, even on the small SBCs, has been able to assume quite a significant amount of RAM, 128, 256, 512 meg of RAM, and significant amounts of flash. Nicholas Peter has done all kinds of work on this over the last few years and has been arguing steadily, and has expressed to me his frustration that no one seems to really taken up the idea that Tiny Linux is valuable, that's important to have it in mainline because you need it to be supportable. But sadly, limited uptake.
I think some folks have done things with it, but not even fed back.
Yes, they've not even fed back. Well, an announcement came out earlier this year, which slide is titled Vindication. There's this product that just came out, the MT3620, which is the first of, I think, what are going to be many products, is exactly what, or very similar, very close to what Nico's been talking about. In this case, it is a single chip solution. It has 4 megs of SRAM. It has 16 megs of flash, which can be directly mapped. It's running Linux on A7 cores. It's got multiple coprocessors, M-class cores that can be used for real-time processing. It is a reasonable cost, so it's not going to be the lowest cost chip, but it fits a particular price envelope that makes sense for some products. And the other interesting thing about this is that it's integrated in with cloud services. So it's not merely just this chip that has restricted resources, but is able to be single chip. And there's all the security benefits that you get out of having a single chip, because you can't probe on the other address lines or anything like that. But it's also integrated with a particular cloud service. Where this is a case where it's not so much that it's an IoT device, but there is a set of services that goes along with that. One of the most important of those, of course, is updates. And the application provider, the company that would be taking one of these chips and building a product, in this particular case, is not the company that would manage the OS upgrades. Now, this is not a product endorsement, but in this particular case, with MT3620, Microsoft takes responsibility for the Linux kernel and for all of the software stack, and managing it, updating it, signing it, and pushing it out for over-the-air updates. So that if you're a device vendor, you have an agreement with Microsoft on how long your device is supported, and then you worry about your application code. And it's designed for multi-layer security, and this is I'm talking about Microsoft, but there is a real use case for those kinds of deployments, especially as the software is getting more complicated. So that's where there's two things that I find very interesting on this, is the fact that it is restricted. With the secure updates, it's really important to have all of the board support, all the chip support in mainline, because it's needing to take advantage of the security updates that are going on in the mainline kernel. It's going to depend on those. It is not in mainline, which is a problem. MediaTek, yep. Yep. And I won't say too much more about that because that's Microsoft product and I don't know too many details, but the fact that it exists and that there are other products of this class that you can project are going to be showing up, that this is interesting, that it's actually valuable to do an open source project around, or to have tiny Linux in mainline and have a robust ecosystem around it. So we've got that, like the work that Nico's been doing for tiny Linux, it's in mainline. A bunch of that stuff has been merged. What we don't have is a project around it of how do you actually, some collaboration of making use of that, of building projects. This stuff is different from most of the distro work. Now, if you're looking at, you get a little bit larger on Linux systems, and then things start to look a lot more like a traditional Linux system. You start to have a full suite of libraries. You start to have possibly package management. It looks more traditional. When you get down to this size, it's not just about the kernel. There is a whole set of libraries that you have to figure out, well, what is it that you need? What is the base foundation? Are all of those pieces also getting the same kind of attention and support to build a system that will fit in less than 4 megs of SRAM? So we started one. We started a project. We're doing this internally to explore. This is very much prototype work, and we want to talk about it. There's lots of opportunity for collaboration, but we've not set up anything. All we've done is we've gone and said, we need this. We're putting together the work. We're building images. Manesh here is going to show some of what we've done. And we put it out in public, right? So it's out there for anybody who wants to take a look at what's already done. And we are interested in if there's interest in creating a project around this, in doing something a little bit more formal or putting some serious engineering effort behind building these kinds of stacks. Ask me questions I can answer. Yeah. Okay. So I just don't want to. Yeah. Yes. 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 We're talking to Microsoft. We're of course talking to Microsoft. Okay. Very good. I don't like to announce other people's stuff. That's all. Yeah. All right. Yeah. But yes, of course we're talking to Microsoft. Microsoft's not the only company that we're talking to. I don't want to call out names, but I want those companies who say they're interested to be the ones to put up their hand to say, hey, I'm interested. That's the only reason I hesitated on answering that question. So what we've done is, where am I at on my slides? Right, so we think there's a whole class of devices that are suitable for this kind of Linux IoT. There's already, the work that's already gone into the Linux kernel is foundational. Having the execute in place kernel, the root file system with execute in place means that we don't have to have nearly as much SRAM. SRAM's lovely, we can have it on chip. It's fast, but we can't have a lot of it. So having it using SRAM means we've got this class of devices is able to exist. Minimize configuration, some collaboration and testing on what the common features are that have to be in the kernel for this class of device. And when I say this class of device, I really am talking about IoT widget that has more than trivial functionality and is always connected to probably to a cloud agent. Not necessarily, but probably. The pieces that are still needed is there's a whole bunch of user space work. We've got we figured out which libraries we need for putting together the demo that we're going to show here. How am I doing on time? So there's the libraries. I'll show you that in a moment. And that's kind of foundational, that actually a lot of those libraries, the things that you're going to need, your libc, libgcc, of course, and let's say libssl or any other of the crypto libraries, those are going to be probably very similar across this class of device. So for this demo that we've put together, we think we've done it with the Google IoT client because it's easy to get access to. We've got it. We can easily build it in and show off this demo. But I think that there's the opportunity here for a foundational project that says, here's the libraries and basic stuff that you're going to need on this class of device, and then have the ability to customize on top of that for specific IoT ecosystems. And we're doing this all on a system guidance platform. So this is, I can't remember what the release status is. We're in process to make sure that it's accessible. It's something that if you're interested in this, you can get a hold of it. It's also not going to be that hard to modify the code that we put out there to get it running on a different platform. We're not using packaging. It's hand built. So these things are so small. Yep. 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 Art.
One kind of question: do you need to revive the MTD XIP code, or are you happy with not writing to Flash at runtime?
That's going to depend on the silicon features. So right now, I'm not sure what we care about with our platform. So of course we provide reference platforms, and I believe we've got write access, or like the hardware would easily be able to support that. For some of these SoCs, you're not going to be able to write at runtime from Linux.
Because we used to have some very sophisticated code that allowed you to write to the flash that you're running the kernel out of. Right. It's all been broken for many years, and I'd rather not revive it. But if we have to, then
I think that's where a project comes into, because there's only so much we can. There's not sure which features are going to be needed, but that's part of why having a project and actually get some people in the room of being opinionated on which things are going to be important. Alex.
On those embedded devices, you want to have an AB boot, because otherwise they're not going to boot up anymore. And in that case, you never want to overwrite the flash or the kernel you're currently running on. You want to always overwrite the B kernel, the one you're not running.
Yeah. There's
the
also...
question is whether that's the same hardware or not, because you can't execute instructions from a DOR flash that you are overwriting in different block.
Yeah. Yeah. So have we got volunteers? Do I have? I've already talked about this. General characteristics of the platforms we're targeting is less than 4 megs of SRAM. I put 8 megs here. I think we're larger than that right now, but I mean, this is new. We're working through what this is going to look like, but this is just so you got a ballpark on the size of these things. It's going to be a mixed A+M design that we're expecting a secure enclave. We're expecting that when you're talking about root of trust, the root of trust is not going to be at the A class. It's probably going to be at a secure enclave that does the verification of images, that protects the flash, and then boots the A class. And then the A class then verifies and boots the coprocessors.
That seems awfully narrow, like the scope of this. I don't know why. What prevents you from making it a wider scope to include things like the other MediaTek chips that they've had in the field for a long time?
Nothing prevents it from being wider. We had to choose something, and we had to make some, because these are so constrained, we could have gone, well, and ARM is really good at this. We'll give you these 200 options of how to build something, which is fine, because I mean, we're an IP company and that's what's valuable. But to figure out what this looks like, it's helpful to really narrow the focus and to make some assumptions about what the design is. But these assumptions I'm holding loosely to, right? So if any of these assumptions are proved to be wrong, or someone stands up and says, actually, this should be that, then great, totally happy with that. Strong opinions weakly held. And I've already talked about it being a common baseline. And there's many IoT agents that could possibly be involved with this. So this is the project. It's up on the git.linaro.org landing team page for ARM. I built it myself, and I've sadly do not write very much code anymore. And I actually got it to build, so it works. It's got the boot wrapper, it's got Linux, it's got BusyBox, uses the device tree for booting. Root file system is a RAM disk. We're using CramFS, but we're not using execute in place yet. Is that right? User space is not execute in place. We do want to get there. There's a set of scripts on how to run it. We load up the Google IoT Core client and just use standard tools. So it's a pretty straightforward project. Do you want to talk through the numbers, or do you want me to? Okay. Okay, Manesh is going to do the demo. What we're at right now for the kernel, we're using it's about 2.8 megabytes for the kernel image. And of that memory usage, what is it, 150K of data, 72K BSS. Is that that's the RAM? Sorry, I should have reviewed this slide more closely, so I knew what I was talking about. So that's the flash image. You go through it.
Yeah. So we are using fast model platform as of now because we have feature for execute in place. The NOR flash is there. So after combine the static memory of kernel is maybe 2.6 MB for text section, which is all execute in place. RAM requirement is very low for us. And if we go to the dynamic memory uses, we have restricted our platform for 16 MB RAM as of now, but as Grant said, we are now optimizing everything, making user space as XIP, and we are hopeful that we'll bring it down as much as possible. And currently user space has, so these numbers are basically restricting you to 12 MB, but what our current system is having 16 MB of RAM. For user space, we have BusyBox, which can be optimized more as like tiny BusyBox or something like that. And we have Google IoT application, which uses lots of libraries like OpenSSL, Crypto, and MQTT, JWT libraries, and we have just cross-compiled those applications and used, cross-compiled those libraries and used with the Google IoT client application, which is written in C. And it does communicates with cloud. Yeah, one more problem where we need help from GCC toolchain team in Linaro, where thumb2 and config LTO does not go, I mean, it does not compile as of now, the mainline Linux kernel, so we need help in that.
A lot.
Yeah.
A lot of help.
Yes. Next.
Huh? No.
So once we compile in thumb2, we'll reduce in memory footprint again. Next is replacing boot wrapper with trusted firmware, which we'll start, I mean, we have started working on it. And then the optimization is still ongoing. Making user space XIP, which is again a big task. It will, I mean, once we decide on the user space, which file system to use, and then we'll start optimizing it. There are some patches, the Nikos patches, some are upstream, some are not yet, but still ongoing process. For example, this LTO feature is fully not yet upstreamed. There are patches which are in review yet.
So I tried LTO before. I had fairly okay success on 64-bit. On 32-bit, I basically gave up because there's so many corner cases I ran into trying to make it work in the general case, in particular around XIP and Thumb2. So I at that point decided it's not worth for me to spend too much more time into getting the LTO patch set to work on 32-bit ARM, because there's all those extreme corner cases.
Yeah, but surely we can follow up on this.
Oh yes, yes, yes.
Yeah.
I know.
It worked for me.
In Thumb2 mode?
Yes, because that's the only way to support the Cortex-M, I think.
Oh, because that's only Thumb2. So the main problem you hit with Thumb2 mode on LTO is that you have some files running in Thumb mode and some in ARM mode, and then you try to assemble that all together, and the assembler gets horribly confused when you mix the .arm and .thumb statements in a file, and it applies to the next file.
So I was going to say, before execute in place gets delivered, I'd be interested to see your DRAM usages with the multiple BusyBox text segments factored out. Because until you have execute in place, then the fact that big BusyBox text segment distorts your memory usage so much that it would be quite nice to see your DRAM with multiple mapped text sections removed. It's a fairly good approximation of what you'll save when you go execute in place.
So as Manish gets the demo set up, one of the things that you'll notice is missing from all of the discussion is there's no talk about what's going on in the secure enclave, or what we do for security. And I think that's one of the things that we see as quite important. You'll need to move that from in front of the projector. There we go. So there's a whole bunch of, some of the next steps as well is figuring out what the secure architecture is, because for these devices, it's not just valuable to have all the software in place, it's also valuable to collaborate on the software update ecosystem, how we do the updates, what the model is for that. And again, that's sort of one of those places where there's a lot of options there, but there's actual value in trying to constrain it down to the way these devices are actually going to be used. All right, are you ready?
Yeah. Okay. So this whole stack is hosted on Linaro tree, Linaro repo, and we have scripts to building the stack and running it. So very basic script so just running the fast model for Cortex A5 with all the components. So this is not a big thing. Let's start. Yep. So we have kept this client application as part of in user bin, and our application is so this is the Google client application, C application, which runs, and this asks for all the various details, device ID, region, and these details will be in the cloud. So I have written the command, whatever project name and blah, 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 yeah. 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 And it will just send a hello world message to cloud. The message has been delivered, and you can check on the cloud as well. So the latest message delivered at 8:56, which is UK time, not here. So, we are basically communicating with cloud with very minimum memory footprint, and I can just run to see the total memory usage.
Okay. And as he's doing that, we've got very little time left, so we'll take a few questions and then take the rest of it offline. Right. So there we go. Questions?
So how do I join in?
We don't have a, how do you join in? We don't actually. We got a Git repository, go and try it, and email us, because there's no project here set up or anything like this. This is research. But if you want to join in, you say that you want to do a project, and we figure out how to do a project. Other
And we
questions?
have a demo tomorrow as well for this Google Cloud, and we will show the complete stack in the posters, and anybody interested, we can discuss it tomorrow.
One question I would like to know if you would consider MMU-less CPUs in the scope of the.
So we've got, again, in the choosing which devices we start with, there's some, we see value in the particular place that we started, but we're not limited to that. And so we also happen to be using A5 cores here, but moving to, is there value on this on 64-bit? Is there value on this for V7? Well, it is V7, ARM7, yeah. We are open to that. I mean, that's all depends on who's involved and on what's deemed important. No one's coming into the room, so we'll take one more question and then shut it down.
More than just a question, I think to the point that Grant made earlier, so the IoT line of business inside of ARM is basically working, we have SDK 700, part of our secure foundations, and we have a number of future customers that are likely to be announcing products over the next 2 years. So you're going to have a number of targets, and what's interesting about it, it's not a full MMU, but the way that it was designed is basically a system-level controller environment, basically a firewall inside that allows you to basically multi-master between the M core and the A core. So the A core can be shut off, M core can still run the security infrastructure and basically continue to run any kind of operations that it's doing with the A core off. So it's a really pretty unique system that we think will be very popular within industrial IoT.
All right, we're done. Thank you very much.